Hey folks, gonna do a video for you here because of my lack of class attendance on the previous Friday, and then we have a campus holiday this coming Friday. So I'll put up a series here. I'm kind of just gonna break them into short clips and hopefully tackle a couple of things in each clip, and it won't be too long to watch. So I'm going to start off here talking about the train example that we did in class, where we had the observers aligned. One was standing in the middle of the train as the train moved past, and one was in a field, and lightning struck, and the lightning hit the field observer. The lightning strikes, light from the lightning strikes hit the field observer at the same time. So I just thought we could revisit that, maybe draw a space-time diagram for it, go on, do a couple of interval examples, and so we'll go from there. So what we have here, right, was the train car moving past at some speed, and someone in the train here lined up with someone out here in the field, and lightning strikes the train, the train tracks right where the wheels are on the outside parts of the train, and then that light, excuse me, that light is moving towards this observer and hits this observer simultaneously. Now, we talked about this in class, and I kind of wanted to get you to the point where we understood that the light hitting this person simultaneously was actually a space-time event. So everyone agrees, no matter what frame of reference they are in, that the light hit this person simultaneously. That's a different use of simultaneity than I was talking about previously. Okay, this is a situation in which we can define this as an event, because if we take the person away, and I tried to kind of motivate this a little bit during the class, if we take the person away and we put a machine there whose sole job is to detect simultaneous light entering from either side, and then it raises a flag, well, if everyone agrees that the flag raises, well, then everyone's going to agree that the light hits simultaneously there. However, what they don't agree on is the simultaneity of the actual lightning striking the track. So as this person moves along, right, they're going to see the lightning from the front lightning strike first as they are running into it, right? And it's going to take time for this one to catch up to it, okay? So while this person agrees that the light reaches them at different times, they're still going to agree that light hits this person at the same time, because from the train perspective, this person is moving this way at speed v. Okay, and so what the person on the train is going to say is that if the person down here sees the lightning strikes hitting simultaneously, what must have happened, because this person is moving this way at speed v, what must have happened is that the front one had to have gone off first, because that light had to catch up to this person, at which point this one then went off, and then the light hits the person simultaneously. That's the in simultaneity with the previous one. So the person on the train disagrees that these happen at the same time, while this person agrees that they do, because this person is located halfway between. These strikes happen at the same distance, and light travels at the same speed, left to right and right to left. All right, so I thought maybe let's draw a space-time diagram of that, and then see if we can pick out those features, okay? Or likewise, make certain that when we're drawing the space-time diagram, we draw those features in, okay? So here is the space-time diagram for Earth, and let's say, so 45, my light line is about here. So let's say that the train, T prime, X prime, going along like that. Let's just make life a little bit easier for ourselves and say that the T prime is the axis of the observer. Okay, so this person and this person are lined up at t equal to 0. and t prime equal to 0. So essentially what that's saying is x and x prime are both 0 there, and right when they cross, they both click their watches to 0, or we agree that it's noon, or however you want to do it, right? Because sometimes you don't want to say negative time. That's fine. Okay, so I'm going to go back here, and I'm going to say, what if we drew the front and rear of the train? Okay, so the front and rear of the train are moving at the same speed as the observer, so let's put those, say, give it a little space and go up like that. So that's the front. This would be the front of train. That's the front timeline, and let's make it equidistant back here. So we're going to start there. Ooh, that's a little curved. It's a little too steep there. Let's go maybe like that. Trying to make them all parallel. Yeah, there's the rear. There's the rear of the train, like so. Okay, now what happens is that light strikes the front and the back of the train simultaneously according to the Earth observer, all right? So we'll just say that happens at t prime equal to 0, right, when they click their watches. That means that for this person, the lines of simultaneity, remember, are parallel with their x-axis. So right here, lightning strikes. Right here, lightning strikes, and for this observer, they occur at the exact same time. Light then travels at a 45-degree angle. So let's get the 45-degree line. It's going about like that, parallel with this one. Okay, hits the Earth observer here, hits the train observer there. So this is lightning from the back strike. Let's see, can you read that? Maybe not. It says back strike, light signal. Right? So in other words, it's the back strike, and it's the light signal propagating going that way. I can see it's not quite parallel with my first one here. All right, well, these are supposed to be parallel, these ones here. So here, if I go like that, yeah, you can see that's a little bit too far over. Okay, I'm gonna go up a little bit more. I want it like that. So like that. Well, anyways, wherever it is, say like that. Now here's the front strike. It should be going at 45 degrees. Okay, there's the front strike, like there. That's the front strike of the lightning. This is the rear strike of the lightning. You can see they're hitting this person at the same time. That's a dot on the space-time diagram. That's an event. Okay. Now you can look at the coordinates of the observer on the train. Here's what they think the lightning strike. Here's how they thought the lightning strikes went. Front goes off first, according to them. Light hits them first from the front strike because they run into it. Well, from the Earth perspective, they run into it first. From their perspective, it went off first. And second one, lightning hits the lightning strike from the back hits the observer in the train second. And from the Earth perspective, it's because that light had to catch up. Now, if you assess simultaneity, okay, from the train perspective simultaneity line is the x prime axis. So all you got to do is think about this thing coming up and down, and you use that to assess which event happened first according to the person on the train. So if I think about this, look, you can see that there's a dividing line here. This one is first. It comes below this axis. If I extend this out here, this one happens second. It comes above. So in other words, I would have to lift this a little bit to get to this point right here. Right? So that means this happened second, this happened first. According to, even we can go further, According to the train observer, that strike happened before they were lined up. Because when they were lined up, that's when x was equal to 0, and that's along this line. That was when t prime was equal to 0, and that was along this line right here. So before the sequence of events for the train observer, from the train perspective, okay, so what's happening? The person here is traveling this way, this way, this way. Oh, not aligned yet. First strike goes off. Aligned, right? Second strike goes off, lined, right? Look at the sequence of events. That happens first. This happens second. That happens third. Okay? So front strike goes off, rear strike goes off, light hits. That's when they're lined up. Okay? So that's what the space-time diagram would look like for the light signals propagating from the train. And that's how you draw a space-time diagram, and also how you interpret them. So, so I think I'm gonna say I will stop this here, and then I'll do another video on the space-time interval with a couple of calculations involved. Alrighty, hope you enjoyed that one.